This looks familiar, doesn't it? Or maybe it doesn't. I don't know. Didn't we talk about one like this? They're just going to ask us a little bit different questions now, but bunch of tables. I mean, it's going to be a ton of tables. So, pedestrian deaths, driver intoxicated, pedestrian intoxicated. Remember what all this means. Let's, in fact, all right. So, okay, so remember what the various pieces, like, tell me about these 61 people here. What do we know about those 61 people? They were drunk. All right, so what about these 61 people? That's right, I got under the intoxicated. They're intoxicated. Yeah, who, though? Who's intoxicated specifically? Yeah, and so these aren't just people. These are accidents in which a pedestrian died, right? And these 61 deaths of pedestrians, sad. In these cases, both the pedestrian was drunk and the driver was drunk. Okay, it might have been Las Vegas. So tell me about these 77. I'll make sure we're clear before we go into the questions. What's up with those 77? The driver is intoxicated, but the pedestrian was not, and yet died in an accident. Right? Right? No, not intoxicated for the pedestrian. Yes, intoxicated for the driver. Everybody seen that? How about these 232? What's up with them? Yeah, the pedestrian's a yes, the driver's a no. The driver was not drunk, but the pedestrian was. And then finally, what's up with these 605? Neither the driver nor the pedestrian, just a sad accident, but nobody was intoxicated. All right, off we go. What's their question? Now, we've done this before. Remember this? It says, I can't even read it there. Here it is back here. If one of these is randomly selected, find the probability that both the pedestrian and the driver were intoxicated. So I'll write it here a little bigger. They want the probability that both are intoxicated. So what is the probability that both are intoxicated? So remember probabilities, the bottom is always the total. Right? It's going to be something over total. Let me move that over. Something over total. And it's going to be both over total. Right? Whenever you do probability, the denominator is like the total things that can happen. Like if I roll a die and I say, what's the chance I'm going to get a 5? Right? It's going to be 1 out of 6, isn't it? Because that's one number out of 6 different things total that can happen. Right? You sort of flip a coin. 1 out of 2 for heads, because that's one of the 2 things that can happen. So the bottom is always the total. So the total, I just add all those up with your calculator, you know. So just this, and this. Somebody have that? 800? Oh, yeah. There it is. 975. It's already there. Thanks. Thinking, nice. You guys are quick. Yeah, 975. So that is the total. Okay, now what's the top? Both. Which group is both? Both intoxicated. What's that going to be? Yeah, that's the 61. That's both, isn't it? Both the driver and the pedestrian. So then just hit buttons on your calculator. 61 divided by 975. They want 4 places. What is it? I'm getting 0.0625. Is that what it is? 0.0625. And is that 4? Yeah. Oh, wait, one more home. 0.06256. 0.06256. Let me write it up here. 0.06256. They want a decimal, 4 places. So there's the 4th place. Remember how rounding works. You circle the place they want you to stop at, the 4th place. You look 1 to the right of that place. If it's 5 or more, you go up, huh? So it'd actually be 0.0626. There's the answer. 0.0626. Are we good there? Questions I can answer on that? So I just circled the 4th place and look 1 to the right. What is that as a percentage? Only 2 places, so it'd be 6.26, right? Remember, percentage has 2 zeros, 2 places. So that'd be about a 6.26%. So in other words, among all the accidents in which pedestrians die, about 6% of them involve both being drunk, both the pedestrian and the driver. So let me put this. But they want the decimal. They don't want a percentage, but I just said that because we're used to thinking percentages. So there we go. Here we go on question 2. And it's very similar, just different numbers. But here's the difference. It's the question. They say, what's the probability that... so probability the pedestrian or driver is intoxicated. So that's what they're asking us. What's the probability that either the pedestrian or the driver... Now, how's that different than the last question? What did they ask last time? And, yeah. Did you notice that? Both intoxicated. That's one word there. Both, which means and, doesn't it? That's the title of this chapter. Did I put it? Yeah, there it is. And or, adding and multiplication. So that's all. Let me just put that banner over tonight. That's basically what I want to help you to master probabilistically tonight. And that is this. Let me just write this up for you. And is multiply or is add. I'd like you to see the truth of it. So, and does not go with add. They're opposites. So, and is multiply or is add. Let's see it in action. So they're saying, what's the probability? So, for probability, the denominator is always going to be the total. And so the total's right there. I won't add them up again. It's right there. 981. So that part's easy. But what's the numerator? Well, let's go through it. Suppose we don't even know that little special rule I just said, and we're just being real. That's always the best thing in all of math, is just to be real with things. And I just went group by group and said, how many of these people, in how many of these cases, was either the pedestrian or the driver intoxicated? How about those 47? Yes. Was at least one of the two intoxicated? Yeah, they were both intoxicated. In these 47 cases, automobile accidents in which a pedestrian died. In those 47 cases, both the pedestrian and the driver were intoxicated, weren't they? So, yeah, they're there. How about these 236? Was at least somebody intoxicated in those 236 accidents? Yes, the pedestrian was intoxicated, although the driver was not. But they're saying they want all the cases in which either the pedestrian or the driver. So they want to count those 236, don't they? Is that making sense? They're saying to us, we want to know all the cases in which either the pedestrian or the driver were intoxicated. And so that would count. Now, how about these 71? Do we count them also? We do, because although the pedestrian was not intoxicated, the driver was. So we count them also, don't we? There are also cases in which either the pedestrian or the driver were intoxicated. How about these 627? No, that's the only group we don't count, because in those 627, neither were intoxicated, right? It's a no for the pedestrian, no for the driver, so we don't count them. So basically we're going to, and just real life, if you just think about these, if I said, out of all these, how many have either the pedestrian or the driver intoxicated? If I just said that sentence to you, just real life English communication. If I said either the pedestrian or the driver, you would naturally add these up. And that's exactly the right thing to do. Any order, doesn't matter. Just add them all up. Does that make sense? Because all those cases, either the pedestrian or the driver are intoxicated. What if they said pedestrian and driver? I want to know the cases where the pedestrian and the driver. What if they said and instead of or? Who would it be? What if they said and instead of or? It would just be the 47. They're the only group where both the pedestrian and the driver were intoxicated, huh? It would just be that. But anyway, they said or, so I'll make sure that difference is clear for you. Yeah, Nashwa.
I don't understand why it's different.
Okay. Hold on, let me finish this one, and then I'll see. Let's add these up. 236 and 47 and 71. I'm getting 354 over 981. And then, when I just hit the buttons on the calculator, I'm getting 0.3. So they want 4 decimal places again, right? They always want 4. So I'm getting, for mine anyway, 0.3 36085. 4 places. Remember how it works? You circle the 4th place. Look 1 to the right. If it's 5 or more, you round up. So 0.3609. That means if you were to grab, among all the accidents in which a pedestrian died, 36% of the time, somebody was intoxicated. See what that's telling us, real life? Either the driver or the pedestrian, somebody was drunk in accidents in which a pedestrian dies. At least if this table is real life. In this study, 36. So somebody asked, in how many cases is at least one person drunk, driver or pedestrian? About 36% of the cases. Making good sense? All right, so what if, let's change the question. Let's do a different version. Well, let's do that version. What if they said, what's the probability? So one more time, was it driver, yes? Pedestrian, no?
Pedestrian was intoxicated.
Who?
The pedestrian.
Pedestrian was.
And the driver was not.
Does it say and in between, or does it say or? So it's really, really big deal. Which is, or driver not. Yeah, pedestrian was or driver not. All right, good question. So let's go through it. We know the bottom is going to be the total, the 981. Let's go, so just go through case by case. So what if they said pedestrian was or, means we're going to add them up, right? Or means add, driver not. Let's go through it. These 47, what do we know about those? Everybody's drunk. So pedestrian was drunk. So we would count them, huh? They fit the category. Right, you're good with the or condition. If I say, you can apply for this scholarship to Fresno State, think with me, let's be as real as we can with this. You can apply for this new scholarship to Fresno State if you've been to the moon, or you grew up in California. You're all in, probably, if you grew up in California, even though you've not been to the moon. Whereas if I say and, I said you can apply for this new scholarship at Fresno State if you've been to the moon and, well, you're already done. If I say been to the moon and, you ain't been to the moon, I assume. And I said and, so you got to do that and do something else, you're already out. You can't apply for that scholarship. Right? Big difference. Or and and. Right? You with me on that? Logically? So if they say or, that means you just have to meet one of the conditions. Been to the moon or grew up in California. It's okay if you didn't go to the moon if you grew up in California. That's what or means, right? Just do one of the two. So these 47 are in because the driver was intoxicated. That's all I need is one condition met for or. Whereas and, you need both, huh? All right, so how about these 236? Are they in? Should they be included in driver was intoxicated? I'm sorry, pedestrian was intoxicated, driver was not. These two, what's up with these two? The pedestrian was, oh yeah, so there we go again, pedestrian was. So they're in. I don't need to hear any more. They're in because it's or. If it's or, you just meet one condition, you're in, huh? How about these 71? Are they in? No for the pedestrian. They said pedestrian was, so they didn't meet that condition. They ain't been to the moon. Did they meet the second one? Driver not. No, the driver is. They wanted driver not. And that 71 people, their driver is. So they're out. They're not part of the group. They ain't been to the moon and they didn't grow up in California. They can't apply. They didn't meet either part of the or. With me logically? So because they said driver not. But then, how about that 627? Now, their pedestrian is no, and they wanted the pedestrian was, so they didn't meet that part of the condition, but it says or, and they do meet the second. Driver not, driver not. So they would be included, 627. Make sense? So just go through case by case and ask yourself if they meet the conditions. If it's or, add up all the ones that fulfill the conditions. Good on that? That makes sense? And then hit the buttons on the calculator. Question 3. A survey of athletes at a high school is conducted. The following facts are discovered. In fact, let me just, I need to make it bigger for you. So here's question 3. It says 85% play football. 85% play football. And 14% basketball. Basketball and 8% play both. 8% play both. Blah, 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 blah. Okay. So there's the key facts. What are we going to do? They're going to ask me some kind of question. What is it? What is the probability that an athlete is either football or basketball? So there's the question. So if you grab one athlete at random, what's the probability that, what was it? What's the probability that they play either football or basketball? So that's the question. So we're talking about the makeup of the athletes at this school. 85% of the, not 85% of the school, but 85% of the athletes play football, 14% of the athletes play basketball, and 8% of the athletes play both. So if we grab one athlete at random, what's the chance, what's the probability that they're going to play either football or basketball? They might not. They might be a baseball player, tennis, whatever. But what's the chances?
8%.
So what we need to do is we need to do exactly what we have here. That is, make a table. We're going to have to make a table to see it. Now notice how these tables are made. So this may be the hardest problem in this homework, because this is the only one where you have to make your own table. There'll be 2 of them on Wednesday night where you got to make your own table. So how do the tables go? Well, you have one characteristic across the top. Doesn't matter which one. I could put basketball there, football there, whatever. This one, it was pedestrian, and a yes or a no. And the other characteristic down the side, like driver, or to be football or basketball, with a yes and a no. So let's do that. So I'm going to make a table. And I'm going to put it like this. And I'll just put football on the top, I guess. Football, and this will be yes and no. And then I'll put basketball on the side, I guess. Basketball's over here, yes and no. Making sense? See how I set it up just like the pedestrian drunk, yes or no, driver drunk, yes or no. And it doesn't matter which, you could have put football on the side and basketball on the top. It doesn't matter at all. But here's probably the most important part. That is, you need to put the totals down here and over here on the right. The totals are really important. Okay, so here we go. 85% play football. Percent means per 100, doesn't it? Right? When somebody writes 85%, it means 85 per 100. Right? That's what those 00 mean, right? 85. Yeah. Anyway, so if 85% play football, where am I going to put that? Could I put that 85 right here? And why not? Yeah, because if I put it right here, I'm saying, yes, they play football, but that's not all I'm saying. I'm also saying, yes, they play basketball. And I don't know that about those 85%, do I? They didn't say, hey, these 85% play football and basketball. If they did, then I could put the 85 right there. But that's not what they said. They simply said they play football. Some of them probably play basketball and some do not. So I can't put the 85 right here. I would be assuming all 85 play both basketball and football. Not a true statement, not what was being stated. Well, then where do you put it? Yeah, right there. You see, it's a total number, right? It's the total yes football number. It's the total of it's total percentage that are yes to football. In other words, whatever number goes here, I'm going to find out eventually, and whatever number goes there have to add up to 85, which we'll find out in a minute. Does that make sense? In other words, maybe, I'm just guessing right now, maybe this will end up being 70%, and this will end up being 15%. I have no idea. I'm sure that's not right. But I'm just giving you an idea of what's going to eventually happen. There's some percentage that play football and basketball, and some percentage that play football and don't play basketball, and altogether it's 85% that play football. Get the idea? I don't know those other boxes yet, but all I know right now is the total percentage that play football is 85%. Let's take the next fact. 14% play basketball. Where's that going to go? Right there. The yes basketball total. Again, they're just saying total percentage to play basketball. Does everybody see that? 14%. All right. Last fact. 8% play both. Where does that go? That's the yes, yes, isn't it? That's what has to go there. Right? Because that 8% play both. They're yes to basketball and football, aren't they? They play both.
You're not putting 85% says football where it says yes football and no basketball?
Right here, 85?
Yeah.
No, because I don't know that 85% is a definite yes to football and no to basketball. They didn't say, let me just stick with it. They just said 85% play football. Some of those 85% play basketball and some do not. Does that make sense? We can't say, if I say to you, they play football, they could play both sports. I'm not saying they don't play basketball. We can't assume that.
Additional information to be in that box.
Right. We would need additional information. We would need to know that they don't play basketball. They haven't said that. So all I can put in for sure is the 85% total play football and 40% total play basketball and 8% play both are in the yes, yes box. And now I can get all the other boxes. Do you see it? Right? If I know there's a total of 85% that play football and 8% are here, what does this have to be? Whatever the difference is, huh? 85, take away 8. It's going to be 77. Right? Because now those will add up to 85. Everybody see that? And the same thing across. 8% plus what makes 14%? Got to be 6, huh? Is that making sense? Now, what about this box? Good job. They got to all be 100. Right? The four inner boxes, right? The four inner, not the totals, not the edges, but the four inner boxes total 100%. Because you got to be in one of those categories. Either you play basketball and football both, or one and not the other, or neither. Right? Every one of us in this room fit into one of those categories. You either play, in high school, you either played both basketball and football. Or you didn't play football, but you did play basketball. Or you played football, but not basketball. Or you played neither. That's me. Played neither. Right? Every one of us is in one of these four categories. So they have total 100%. So whatever. So just subtract from 100. So whatever. What is 8 plus 6 plus 77? I don't know. 8 plus 6 plus 77. What is that? 91? 91. So this leaves 9% left over, huh? To make 100. Then I just take 100 minus 91. Gives me the 9%. Which I put right there. Is that good? So this isn't easy, is it? This will be on YouTube. Watch it back. Now let's finish. You can finish the others. We don't need to. We're probably ready to answer their question now. So grab one athlete at random. What's the chance they play either football or basketball? So what's the chance if you grab one of these at random? What's the chance they play either football? Let me get this out of the way now so we can have some more room to work. So is that an and question or an or question? And here's the big, bad, little, tiny, but powerful or. So that means I'm going to add up a bunch of categories, right? Whenever they say or. So which categories am I going to add up? Those three. Because those three are either football or basketball. right? Like these 8% here. They played both. So they played either, you think about the scholarship. You can apply for the scholarship, you've been to the moon, or grew up in California. You can apply if you grew up in California. Or you just meet one condition, right? Right here. These 6%. They did not play football, but they did play basketball. So they're in, right? It said either football or basketball, either the moon or grew up in California. These 77%, yes, they played football. So they're in. I don't even need to think about basketball. The only people that are not in is the 9%, because they played neither football nor basketball. So they're out. So it's 8% plus 6% plus 77%. And we don't even need to divide because it's already out of 100%. It's percentages. So that's kind of nice. You don't have to divide. So what is that for? Is that 91? 91%. So 91% played either football or basketball. How we doing? Questions on that one? Okay, so question number 4. A store manager gathers some data on store's customer, age-related, blah, blah. Here's the ages of customers at their store. So look at the age information over here. What does that say right there, that little part I circled? What is that? Less than 20, right? So the age of customers that are teenagers, basically. 19 and below, right? They're less than 20 years old. How many customers that are less than 20 years old came into their store? 85. How many customers in their 20s? 79. How many customers in their 30s, etc., etc.? Making sense what the table is saying? Let's go to the questions. What is the probability that a customer is at least 20 but not older than 49? So, again, one customer is chosen at random for a prize giveaway. Just like Las Vegas, they're just giving away all kinds of things because they're taking everything you got. All right, so what's the probability that the customer is at least 20 but no older than 49? At least 20. So here, this is more about language than anything else. Being super clear on these words. What does at least mean? If I say I've got at least 3 coins in my pocket, I've got at least 2 pens in my pocket. That's true. I've got at least 2 pens in my pocket. What does that mean? Yeah, 2 or more. Right? If I say I've got at least 2 pens in my pocket, I could have 2 or 3 or 4 or 5. I could have 10 million. 2 or more. At least 2. We 100% clear on that? So at least 3 means 3 or more. So you got to be really, really clear on the language, which is valuable for reading technical information. So at least 20. So what does at least 20 mean? 20 or more. So what's the probability the customer is at least 20, so their age is 20 or more, but not older than 49? So that's 20 to 49. What's the chance that so A is basically saying 20 to 49. What's the chance the customer's in their 20s, 30s, or 40s? Is basically what they're asking, huh? And so what is the chance they're in their 20s, 30s, or 40s? Those 3 categories added up over the total, because probability is always over the total. Did they tell us the total? I don't think so.
No.
So we got to do our own adding for our own total.
Yep.
How many? Well, you probably have different numbers, or
487.
Is that what it is? Thank you. 487. So then it's going to be whatever 79 plus 98 plus 59 over 487. Then just hit the buttons on your calculator. Is that good? I'll go on to part B. Get the idea there? Part B. What is the probability that the customer is either older than 60 or younger than 40? Older than 60. How many people are older than 60? It's 88. And it says or. What do we always do with or? Or means add. That's the theme of the night. Or means add. And means multiply. Or, so 88 plus. I'll put it over here. 88 plus. Younger than 40. How many are younger than 40? Well, that's those three categories, isn't it? So it's going to be 88 plus those other three. Kind of run out of room here. It's 88 plus those other three categories. 85, 79, 98 over the total. What was it? 487. Hit the buttons on your calculator. Is that good? Is making sense? Am I going too quick? Is this good for you? All right, let's do D. Let's see. What is the probability that a customer is at least 50? At least 50? So it'd be those two categories, huh? At least, again, least means that or more. So,
I know what I do have different numbers than you.
So this would be 86 plus 88 over 487. Then just hit the buttons. How we doing? We good there? Questions I can answer? Okay. According to Master Foods, the company that manufactures M&Ms. I like M&Ms, especially the peanut ones. 12%, it's the healthy M&Ms, right? 12% of peanut M&Ms are brown, 15% are yellow, 12% are red, 23% are blue. They're not even Steven. I didn't know that. I wonder if this is right. 23% are orange, 15% are green. Okay. So compute the probability that a randomly selected peanut M&M is not green. I was just saying to my wife in our long drive back last night, as she kindly handed me another handful of peanut M&Ms. We had this big bag. I love peanut M&Ms. They are the perfect snack. All right, so what's the probability that a randomly selected peanut M&M is not green? So if you randomly grab one peanut M&M out of the bag, what's the chance it's not green? So subtract 100 from what's that? You might. Do you have different numbers you do in your numbers instead of mine? Or so you're saying I got to subtract 100%, take away what?
The 20%, 23%.
Where are you getting the 23%? That's blue.
I'm sorry, the 15%.
Gotcha. Yeah, the 15% that are green, huh? And that makes perfect sense. 85%. Yeah, everybody see that? Right? If 15%, it'd be like me saying there's a 15% chance of rain tomorrow. So then what's the chance it won't rain? Whatever 100 minus that is, huh? That's what we're talking about here. If they say, what's the chance that the M&M you grab is not green? Well, there's a 15% chance, 15% of the M&Ms are green. Then subtract from 100, 85% are not green. There's an 85% chance, that's the probability, that you won't get a green one. Now we're gonna go a long way with that not. Make sure that makes sense in problems to come. We're do some tricky stuff with not. Make sure the not, the opposite ideas landed on you. I'm glad to talk more about it. Compute the probability that a randomly selected peanut M&M is blue or brown. Blue or brown. What do we do with or? Add. So I just take the blue. What's my blue number? Oh, there it is, 23%. Add the brown number, 12%. And whatever you get there, 35%. Good so far? How about next? What if you grab two randomly selected peanut M&Ms? What's the chance they're both orange? So, yeah, both orange. That's going to be 23 and 23. that make good sense?
Do we just turn these to decimals?
Yeah.
Oh, do they want decimals? I didn't even realize. Okay, yeah, I didn't. How did they say so?
Yeah.
Oh, down below the screen. Is that what they said?
It says round your answer to 4 decimal places.
Oh, yeah, you're right. I'm just not even seeing it right there. You're right. Thank you, Robin. 0.85. Yeah, that should have been 0.85. Yeah, they want decimals, huh? So that should have been 0.35. That should have been 0.85. Thank you. I didn't read the fine print there. So, right. Okay, so let's get back to this C. The C, so if you're looking at something else, dial in with these. C is a big deal. We're shifting gears at C. Something's up with C. What's on the screen is dead wrong. Why? Well, first off, does it just, I'll show you the steps and everything. Think about this for a minute. But even better, you know what's the best thing to do in math? Best thing. I'm somewhat of an authority. After 25 years, I've taught, I don't know how many, lots of students dealing with math, watching people think about math. If somebody say one sentence, what is the number one advice you get to somebody to do better at math? I would say, be real with it. Be real. Make sure it's real to you. And not just numbers on a page and you're just like moving around numbers. If you're real, you'll be surprised how much you know. You really do know a lot of math. What do I mean by real? Well, just be real with me. What if I said, hey, I got this bag. Just think as real as you can with me. I got a bag of M&Ms. I had one in the car last night. I got a big family-sized bag of peanut. My wife and I take snacks on the road. Big family-sized bag of peanut M&Ms. If I said, hey, 23% of that bag is, whatever it is, orange. Orange. So if I reach in there to just get one, let's just start with one. I'd have a 23% chance of getting an orange one because 23% is orange. So would it be more likely or less likely if I reach in, say, honey, I'm going to reach in, I'm going to grab 2 at random. I said, I'm going to reach in and I'm going to grab 2. And I'm hoping to get both orange. I reach in blindly, grab 2. Is that more likely, easier to have happen, or less likely, which would be more surprised, than if I'm just going to reach in and hope I get one orange? Which is easier to do? Just get one, right? We all sense that, don't we? It's easier to get one orange one than it is to reach in and get 2. Right? So the probability of getting 2 has got to be lower, not higher. You can't add those. That can't be right. Right? You with me on that? Right? You feel that you do, right? You feel that. Don't deny those feelings. Those are good feelings. I want to put you in touch with those. Right? So again, one more time, make sure it's clear to all. This is the best thing. It is because, there's so many rules in math and, but what'll help you if you're in the middle of an exam and you're like a little fuzzy, just be real. Be real. Just think, if I was to reach in the bag and just grab one orange one, okay, there's a certain chance of that, would it be harder or easier to reach in and grab 2 orange at random? That would be more surprising, wouldn't it? That would be harder to accomplish. So the percentage of that's got to be lower, not higher. So we can't add them. That can't be right, can it? Yeah.
So on the orange ones, peanut butter or peanut ones too?
Oh, the whole bag's peanut.
Oh, okay.
The whole bag's peanut. They're the best kind of M&M. They're healthy. They got the nut in there. All right, that's my opinion anyway. It's funny. I didn't know this problem was here, but I was just saying that last night. Anyway, all right. So we can't add, right? So that'll catch you. That reality, that's what's meant to catch you. If you're not being real with math, then it's like walking a tightrope, no net. No net. If you're not being real, you just make one false step. And you're going to fall to your death on that problem, I mean. It's a little dramatic. But you know what I mean, right? Whereas if you're being constantly real with yourself as you're doing math, thinking about real bags of M&Ms and real chances of doing things, when you start to add these up, you'll stop yourself. You go, nah, that can't be right. It can't be more likely to get 2 than 1. And then you stop and you give it a second thought and you catch yourself. That net the net of reality catches you. And say, okay, so and that is, over my 25 years, that's what I've seen people do who are more successful at math. In all my thousands of conversations with hundreds of thousands of students, what the pattern I've seen is that people that are more real about math catch themselves when they start to do something wrong on an exam. And they go, oh no, and they correct. They're not people with a perfect memory or people that, are flawless little robot math machines. No, it's real to them. It's real. So, okay, so it can be more real to you. Just get yourself into reality. You all sensed it once I talked it out with you. So, okay, so we can't, now let's get back more to the rules. So that reality is supposed to catch you. Go, oh, wait. Something's not right here. Now, what were those rules again? And is multiply or is add. Both orange. Both orange. Is that and or? If I said to my wife, honey, I got 2 orange ones. I got them both orange. Would she say to me, do you mean you got the first one orange or the second one orange? We would not have these weird conversations, but you know what I mean. It would mean, she would know what it means. I got the first one orange and the second one orange. This is and. Both means and, doesn't it? And is not add. It's multiply. We're supposed to times these. That's what we're doing wrong. We were adding them like it was an or. It's not an or. Both means and. Doesn't it? They snuck in an and one all of a sudden. So how do you do that? We got to make them decimals, right? So this is going to be 0.23 times 0.23. Hit the buttons on your calculator. Right, we always change the decimals when we do operations, right? I'm getting 0.0529. About a 5% chance. And that fits our feeling, doesn't it? It's got to be a lower chance. It's harder to get both orange than just one. That looks like reality, doesn't it? So, and is multiply. And both means and.
What if it says 3? Yeah, all.
You got it, yeah. Multiply 3 times 0.23 times 0.23 times 0.23 again. It'd be even harder, wouldn't it, to get all 3? And that number would go even lower. Why are the numbers going lower every time we multiply them? Because we're multiplying by something less than 1. When you multiply by a decimal less than 1, you make things smaller, don't you? Right? We good? On with D we go. If you randomly select 5, Peter, that none of them are red. Okay, yeah. So if you're going to reach in and randomly grab 5, what's the probability that none of them are red? Can I say just a obsession with cleanliness? But you pour, you don't reach in, but I'm saying reach in anyway. So if you reach in or you pour and you randomly get 5, what's the probability that none of them are red? What's the chance that none are red?
I feel like it's easier to find the probability that 5 are red and subtract
That 5 are red?
Just to multiply them 5 times and then subtract that from.
Probably that none are red. Here's what we have to do. We have to fashion this as an and question or an or question. Because that's what the sections are. That's what you should be thinking as you're doing this homework. This is either an and question or it's an or question. So I want to say something which is logically the same meaning as this by way of and or. That's the real battle. Can you do that? Let's think about that. How can you say this? What if I said I reached in the bag and I should have poured, but I reached in the bag and I got 5 of them and none were red?
Then you can say it could be brown or yellow or blue or orange or green.
Yeah, the 5 of them are all those colors, huh?
Right. Would that be an or?
That would be or, but that would be impossible to, not impossible, but very difficult to do. Because how would you do that then? So you're right. You're right what you're saying that we could do, or you're saying, well, if none of them are red, then all of them are, the other colors, whatever, brown or blue or whatever. True. But I don't know the probability of all 5 at once. So in other words, what I want to do, and I should cut to the chase and then it'll make more sense. The first has to be not red, right? And the second, not red. And the third, not red. And the fourth, not red. And the fifth not red. That means none are red. Right? If the first is not red, and the second is not red, and the third is not red, and the fourth is not red, and the fifth is not red, that means none of the five were red. So there it is with and. What does that mean we're going to do? We're going to times those. So what is the probability that the first is not red?
Minus whatever red is.
Yeah. It is, what is red at 12%? So this is going to be 100%. I need a fresh screen here. It's going to be 100. It's going to be, so not red. Let me just do that first off. Not red for just one not being red. Just one at a time. If you just grab one and you want it to not be red, what's the chance of that? It's 100 minus the 12% in the bag that are red. That would be 88%. Not red. 88% of those M&Ms, those peanut M&Ms, are not red. Right? So when I reach in the bag and grab one, the chance that the first is not red is 0.88. And the chance that the second is not red is also 0.88, etc. You're just going to multiply 0.88 by itself 5 times. Does that make sense? So we did do the opposite of the 0.12. If you're thinking opposite now, yeah, let me hold on. The next question is going to be the opposite of the opposite. I'll show you. We'll get there. But let's hold with D for a minute. So everybody tracking with me on D. Right? 12% are red. So the chance that one is not red is 88. Multiply that you want all 5 to not be red. So multiply those together on your calculator, whatever that, yeah, I'll just move on. Whatever that, because, well, no, actually I want an answer. So, do you guys know about the power button? The up arrow button? That'll do it for you. You can just type 0.88, up arrow 5, hit enter. That's to the 5th power. That means multiply 0.88 by itself 5 times. That'll save a little time if you don't have to. I'm getting an answer, which is 0.5277. So that's the probability that I get 5, none of which are red. Hey, does that feel right? I really encourage you to stay in reality. What do I mean by red? I mean, what if I'd got 99% chance? That wouldn't feel right, would it? 99% chance that none of them are going to be red? 50%? Yeah, that feels about right, doesn't it? Do you have a sense of that? About half the time you reach in, don't got a red one out of 5. About half the time you do. Feels about right. All right, let's move on with E. E says, if you randomly select 5 peanut M&Ms, good probability that at least one of them is red. At least one of them is red. So now you're reaching in, grabbing 5, and you want to know what's the chance that at least one is red. What's that? What is it? Or at least one is red. Yeah. What would be the, if we did or, at least one means 1 is red, or 2 are red, or 3 are red, or 4 are red, or 5 are red. We could do that, it'd be a lot of work. There's an easier way. Look back at D. How does it relate to D? Do you see how it connects with D? What was D? What is this 0.5277? What is that? Probability that what? None of them are red. What if I reach in the bag, grab 5, look at them, and my wife says to me, hey, are none of them red? And I say, nope. What does that mean? If somebody says to me, are none of them red? What does that mean? If she says to me, are none of them red? And I say, no. What's the opposite of none being red? One or more are red. E is the opposite of D. Do you see that? The opposite of none being red is 1 or more are red. Isn't it? Do you see that? How we doing? Let me say that again. What if I said, what if you guys said to me, did no one get A's on that first exam? Are nobody getting A's? And I said, no, that's not true. What does that mean? One or more people got A's. That's the opposite of nobody getting A's. The opposite of no orange, or the orange, yep, no red M&Ms is one or more red M&Ms, isn't it? Do you see, E is the opposite of D. So what do I do to get the answer for E then? What does it mean if it's opposite? With percentage, if I said there's a 20% chance of rain tomorrow, what would be the chance it won't rain? 80. And you're getting that by 100% minus. What if I gave it to you in decimal? What if I said the chance of rain tomorrow is 0.20, the decimal version of 20%, same thing, right? What would you do decimal? If I said the chance of rain tomorrow is 0.20, what's the chance it won't rain? You'd take it from 1, you get 0.80. 1 is the same as 100 in the percent world, right? 1 in 1.0 decimal, you can make it 1.0 if you want, same as 1. 1.0 decimal is the same as 100 percentage, isn't it? They're exactly the same, right? 1.0 decimal, if you move that 2 to the right, it becomes 100 percentage, doesn't it? So it would be 1 minus 0.5277. Right? If 0.5277 is the chance that none are red, then the opposite, 1 or more are red. Take that away, you're going to get 0.4723.
How would you do that if you didn't have D, though? Would it be easier just to flip it and do D? Like if you didn't have that 0.527.
Right, I would do it. And you'll see, we'll do some of those in a bit.
Okay.
I would actually do D, even if they hadn't made me, because that's the easiest way to go. Question 6. You toss a fair coin 4 times. What's the probability that you get all heads? So you toss a coin 4 times. What's the probability that you get all heads? Let me give you a second. Do you have a thought? A coin 4 times, what's the chance you get all heads? 4 heads in a row. Yeah, so the chance of getting 1 heads is certainly 0.5, huh? We all agree with that, right? Half, 0.5. But how do you do 4 heads in a row? Is that and or? If I said I got 4 heads in a row, does that mean I got a heads or a heads or a heads or a heads? Or does it mean heads and a heads and a heads and a heads? And, right? Doesn't it mean and? It means you got a head, and then you got another head, and then you got another head, and then you got another head. And what do we do with and? Multiply. It's getting easier? 0.5. And you could just do to the 4th power, right? That means 0.5 times itself. You don't have to do the power. If you want to just take 0.5 times 0.5 times 0.5 times 0.5, that'll do it. Or 0.5 to the 4th power. I'm getting 0.0625. 0.0625. So is everybody good with part A? We good with part A? Does that make sense? Now, how about part B? You get at least 1 tail. So you're going to flip the coin 4 times, and you want to get at least 1 tail.
Is it 1 minus the top?
Good question. Najwa thinks it's 1 minus the top. Is she right? She's a probabilistic genius. That's exactly what it is, right? Does that make sense? Because it's the opposite, isn't it? What's the opposite of getting all 4 heads? You say, I did not get all 4 heads. What's the you can get all 4 heads or not all 4 heads, which means what? At least 1 was tails. Isn't that not getting all 4 heads? Right? You tracking with me? So you can get all 4 heads. Or what if you don't get all 4 heads? Well, that means there's a tail, at least 1 tail somewhere in there. See how that's the opposite? It's the opposite. So they're gonna keep hitting that drum. You really want to get that concept. They're going to hit it and hit it and hit it and hit it and hit it. Because it's really central to probability. The opposite of at least 1 is none. Are you getting the hang of that? If I said, did at least 1 person get an A on the test? For sure. If I said no, that would be nobody got an A on the test, right? At least one means one or more. The opposite of that is none. So if they say at least one tail, one or more tail, that's the opposite of no tails, meaning all heads. So subtract that, you get 0.93, what? 75. 0.9375. We good? Starting to make more sense? So at least one is the opposite of none, isn't it? 8. Blah, 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 blah. Let me cut through the words. Basically, when they really do this, when they test for diseases and things, and they combine samples to save time. Maybe you know about this. So basically, what they're saying is they'll take when blood testing for a viral infection, it's more efficient, less expensive, combining samples. So they'll take samples from 3 people, they'll combine them, and if it comes out negative, they know they're all negative. Does that make sense? So they'll take blood samples from 3 people, they'll throw it all in the same whatever dish, they'll test it, same petri dish or whatever, they'll test it. If it comes negative, that means all 3 of them were negative. But if it becomes positive, that means 1 of the 3, or maybe 2 of the 3, or maybe all 3 of the 3 were testing positive for the virus. That's why the pooled together came out positive. Getting the idea? So let's think what that means then. When they do that, they got to know the probabilities involved. So assuming the probability of an individual blood sample testing positive is 0.1. So let me write that. Probability that an individual is positive is 0.1, 0.1. So if the probability of just one sample being positive is 0.1, what's their question? Find the probability of a positive result for 3 samples. So what's the probability of a positive for 3? So be as real as you can with this. Do you real life understand what it is they're saying? So rather than just diving in and moving numbers around, that's not a good plan. Stop and check yourself. Make sure that you really do grasp. For example, if somebody's to ask you, talk for 5 minutes about what's even being done here. Talk for 5 minutes about what this is really asking. Could you explain? Do you know what they're even saying? What does this mean? Probability positive for 3. Does that mean all 3 are positive, for example? So that's not what they mean. Did you understand the words up here and what was really going on? You really have to understand the gist of it. Of the battle on these is being real with them and understanding what all the words mean. It's a lot of reading comprehension at this point forward in the course. Do you understand what they're talking about there? They're saying, remember what they're doing. They're grabbing 3 blood samples, and to save time and money, they don't want to test each one individually. That just takes too long, especially for something that's a rare condition, something that most people don't have. They just want to save time and say, look, let's just dump them all in the same thing. Probably nobody has it anyway. Let's just dump all 3 in the same dish and test all 3 at once, in one pooled sample. And if it comes out negative, we know none of the 3 had it. That's what usually happens, because most people don't have this thing. Only 0.10, only 10% of the people have the thing, right? 0.1, 10%. So, what does this right here mean? Positive for all, positive. What's the chance you're going to get a positive result for 3 of them thrown together? Maybe I should write out more words there to be more clear. What's the probability of a positive result when all 3 mix? Yeah, I should just be more clear, write the words like that. That's what they're saying. What's the chance of a positive result when all 3 are mixed? Is that an and or an or? Well, you could kind of phrase it either way. If we tried to phrase it as or, we're going to run into trouble. Why? Well, just think real life. How would you try to say that as an or? You're going to mix all three together, and you want to get a positive result. Well, you could say the first one's positive, or, well, anyway, I don't got time to go through all the wrong paths. Let me just dive into the truth. The truth is it's the opposite of all three being negative. That's what it is. So the opposite question is all three negative, right? If all three are negative, then when you mix them together, the thing will come out negative, right? So what's the chance that all three are negative?
0.729. Right?
Yeah. How are you getting that?
The 9% or 90%.
Yeah. Yeah, because this is 0.1. It's the probability that an individual test is positive. So then the probability that an individual is negative must be 0.9. Huh. Right? If there's a 10% chance that one is positive, just one by itself, then there's a 90% chance that one by itself is negative. Negative. Right? That's the opposite of positive. So there's a 90% chance. If there's a 10% chance of one coming out positive, there's a 90% chance of it coming out negative. If there's a 10% chance of rain tomorrow, there's a 90% chance it won't rain. Right? If there's a 10%, this 0.1 is the same as 10%, isn't it? If there's a 10% or a 0.1 chance of positive, then there's a 0.9 chance of negative. Okay, so what? Well, I want all three negative. All three means and. So the first negative, and the second negative, and the third negative. What's the chance that all three are negative? 0.9 times 0.9 times 0.9, which is 0.729. Your calculator will tell you, as you said. 0.729. That's the chance that all three come out negative. The first is negative, and the second is negative, and the third is negative. This making sense? Where am I losing you?
Where did you get 0.9?
From the 0.1. So if there's a 0.1 chance of rain tomorrow, what's the chance it won't rain? Opposite, right? If there's a 0.1 chance of positive test result, then there's a 0.9 chance of negative, isn't there? For one, just for one. Right? You with me on that? If there's a 0.1 chance for an individual coming out positive, then there's a 0.9 chance of an individual coming out negative. Right? Want me to step back again with this? I know there's a lot to do, but so again, see what they're saying right here? The probability of an individual, just one of them, coming out positive is 0.1. Yeah.
Okay, I have 0.07.
So, yeah, so 0.93. So if it was 0.07, if there was a 7% chance of rain tomorrow, what would be the chance it doesn't rain? Right? So just subtract from 1. Whatever they give you, just subtract from 1. The opposite is always subtracting from 1. Is that good? So yeah, so let's just change the problem. What if they said there's a 0.07 chance of being positive? Well, then what's the probability of an individual being negative? Be 1 minus that, be 0.93. That's for just one. And so then if you want all three to be negative, so all three coming out negative would be 0.93, 0.93, 0.93. That, hold on, we're not there yet. Let me wrap this up first. So that would be all three negative. So you would hit the buttons on your calculator, right? And that would come out 0.00, no, I'm sorry, 0.80, 0.804357. Now that's the chance that all three are negative. And then the opposite of that is the chance that one of them became positive. Are you tracking with me? Do you see that last opposite? Right? This is the chance that all three, or what if I said, this is the chance that the next 3 days there'll be no rain? Let's do the rain thing again. Well, it said the next 3 days, no rain, no rain, no rain. Here's the chance, 80%. Okay? If I said there's an 80% chance that the next 3 days, no rain, no rain, no rain. So what's the opposite of that? What if I take 100 minus that, I get 20%? What's the opposite of no rain, no rain, no rain?
Rain at least one day.
Rain at least one of those days. Doesn't have to be raining all three. Somebody said, hey, the next 3 days, will it not rain for the next 3 days? I said, well, no, that didn't work out. That means one of those days, or maybe two, or maybe three, but at least one, it rained. Right? That's what we're doing with this, these test results. They're saying, what's the chance that in the end it comes out? Find the probability. You got to remember their question. After all this talk, it said we could lose their original question. Find the probability of a positive result for the three samples combined. Positive for all three combined. Which means just one of them has to be positive, right? Did you read all those words in that paragraph and understand them? They're saying when they dump those three blood samples together into one petri dish, if any one of them had the virus, then the whole batch will test positive. So that's the opposite of all three being no, 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 isn't it? If the chance that all three are negative is this, then the opposite of that is 1 minus. Like that, which comes out 0.1, whatever it does, 0.195643. And then round it on that. So question 9. So in a large population, 67% of the people have been vaccinated. If 3 people are randomly selected, what is the probability that at least one has been vaccinated? So let me write out, get rid of question 10 here. Let me write out a game plan for at least one. At least one means 1 minus, well, let me try that again. The probability of it. We've had several at least one questions now. Let me write out a game plan for you when you see at least one. The probability of at least one is 1 minus the probability of none. Because that's the opposite. The opposite of at least one is none, isn't it? Right? If you guys asked me, did at least one person get an A on the first exam? If I said no, what does that mean? No one got an A. That's the opposite of at least one, huh? The opposite of at least one is none. So when two things are opposite, then one of them comes from 1 minus the other. So how do you do at least one? 1 minus, and what's the probability of none? How do you do the probability of 1? Not the first times not the second times not the third, etc. So there's a formula. There's a general setup for how you do the probability of at least one. You take 1 minus, not the first, not the second, not the third, multiplied together. There's a D here. All right, so on this one, 67% of the population have been vaccinated. If 3 people are randomly selected, what is the probability at least one has been vaccinated? Well, at least one is going to be 1 minus, not the first. What's the chance that not the first person has not been vaccinated? 33. Right. There's a 67% vaccinated, then subtract from 100. And you get 33% not vaccinated, huh? If 67% have been vaccinated, then 33% have not. So this will be 0.33 times 0.33 times 0.33. See how that's not? Is that making sense? That's the chance that the first person has not, and the second has not, and the third has not. So that's the chance that all 3 have not, and the opposite of that is at least one has. So it's 1 minus, whatever your calculator says at that point. I'll leave it at that. I better move on. So there's a general formula for how you handle probability of... Okay, so here we go. Here's grades and gender. So how some different people did on some test. Let's make sure the tables you want to put that table in your notes or just follow along with me. So 3, what does that 3 represent? Males that got an A on the test, huh? And that 4? Females that got an A on the test. 9? What's that 9? Who?
Males that got a B.
Males that got a B, etc., etc. We good? All right, so here come the questions. If one student chose random, what's the probability that they were a female? If you just grab one student at random, what's the chance they were a female? It's going to be female over total. Right? And that's going to be 30 over 55. Hit the buttons on your calculator and get a decimal.
5454.
Okay, I'm just going to move on. Good so far? Next question. Probably they were a male and got an A. So if you're going to grab somebody at random out of that group of 55 people, what's the chance that that person will be a male and got an A? What do we do? Male and got an A. How many people are male and got an A? 3. Right? Aren't they the only ones that are both male and got an A? So it would be 3 over 55. Beautiful. And then hit the buttons on the calculator. C. Male or got a C. Now it's or. What do we do with or? Add them up, huh? Male or got a C. Ooh, so it's going to be out of 55 again. That's the total. But male or got a C. How are we going to do that? There's a couple different ways to go. Yeah, you could just grab the total male number, 25 total males, huh? Which comes from 3 plus 9 plus 13. You could just add those up, or you could just say, look, it's already added up for me. 25 total males. But they said male or got a C, so you got to add those up, huh? So what should I add to that? What am I going to add? The 21. Zach, why do you say the 8?
Because you already have the 13 in there. They're not different people.
Can't just add this 21. Right? Because you're double counting those 13. Right? Right? What is this? You basically, here. So this is why I would suggest, honestly, I think it's easier just to ignore all the totals and just go, it's these people, these people, these people, and those people. I think that's easier, more clear, less likely to make a mistake. Those are the groups. That way you don't mess with totals and worry about double counting. Just say, look, it's those are all the males, and then the other people that got C's. Those are all the males or females that got a C. So that's the chance that it's a male or got a C. So I think that's easier, just add those up, which is the same as the 25 plus the 8. If you understand all that, that'll work too. But you got to be careful not to double count. Add all that up, is that 33? Over 55? I think, 21, 30. Yeah, and then hit the buttons on your calculator. I think it's 0.6. Anyway, let's go on to D. Now this is the one I really want to show you on this example is D here. If one student is chosen at random, find the probability that the student got a C given they are female. So probability that they got a C given that they're female. That's what we're going to talk a ton about on Wednesday, is given. So this is our brief introduction. What do you think about that? If you grab somebody at random out of this group, what is the chance that they're somebody who got a C, given that they're a female? So when they say given that they're a female, what they're saying is It'd be like if I played this game with you guys. If I said, hey, I just grabbed a student at random off my roll sheet, and what's the chance it's somebody that got a C on the first exam? Let me give you this information. It is a female. That's what they're saying. Given that it's a female, they're giving you that information. You know it's a female. Well, who's not in the mix anymore? All these guys. They're out. It's none of them. You see, what given does is limits the possibilities, doesn't it? It's not out of just anybody now. It's only out of the females. So out of these females, that's my whole group now. So that's my total on the bottom. It'd be 8 out of, whatever. 30, huh? Yeah, we can just do 30. Yeah, you're right. It's right there on the screen, huh? 8 out of 30. Exactly. It's just 8 out of 30. Does that make sense there? Can you read that? 8 out of 30? Make that a little nicer. Right? Because it given limits who you're talking about. We're given that it's a female. How we doing? Is that good? Then just hit the buttons on your calculator. Let's check one more out with our last 2 minutes here. So a jar contains 8 red marbles. So there's red that are 1 through 8, and there's blue that are 1 through 10. And you're going to pull out a marble at random. What's the probability it's a red marble? So if you have this jar full of these 8 red marbles and 10 blue marbles, and you reach in at random, blindfolded, don't look or whatever, and you grab out, what's the probability you're going to get a red marble? So 8 out of 18. Because there's 18 total marbles, right? 10 blue, 8 red. 18 total marbles, 8 of them being red. Divided on your calculator. What's the probability it's an odd numbered marble? How many odd numbers are there? Yeah. Odds are like 1, 3, 5, 7, right? Give me that. 1, 3, 5, 7. Those are odd. So, it's just going to be half, isn't it? Half of them are odd. Half of them are odd. What's the probability that it's red or odd? Red or odd. Or, are we going to add or multiply? Add. So how many red ones are there? There's 8 red ones. And then how many odd ones other than the red? We don't want to double count. How many odd blue? 5. Because half these blue marbles out of 18. Is that making sense? Red or odd. 8 red ones. 5 other ones that are odd. 13 total marbles are either red or odd. All right.